Okay, let's continue. So this is continue of previous this slide, and what can be the features, word shapes. So for example, you can specify if that it contains some this kind of capital letters in word. So it can also be some feature. You can specify it. So for sequence models, okay, we can. Oh, this is maximum entropy. So it's kind of like logistic regression continuation. So you find out algorithm it was used previously. So it has web Gerundi. So for example, you have this text chasing opportunity in an age of upheaval. And for example, Murdoch discusses future of news corporation. So this is for post tagging part of speech. If it is verb, this is noun. This is in determination, noun, in, and etc. And for example, for word segmentation, etc. We can specify, for example, context, and this is shows how you can make it. So for example, for this point, for this, the dough fell 22 and 6. So what you can do, you can say this can be the features, word 0, 22 and 6, so itself, the word itself. The next feature is next word, percent, -1 fell, t -1. So what was the previous words part of speech? So it was verb in past. And t1 -21, so it's also, you can specify the noun, noun, phrase, verb d, and has digit, true, and etc. So you can find out them. And post tagging, so same for post tagging. If you know, if you want to find the if it is preposition or verb or etc. And so we do not need this one in this thing. And let's continue with, no, not Elmo, but for this thing. So this is continuing of the previous Word2Vec topic. In Word2Vec I can actually rewind you some topics. So Word2Vec was when you want to represent the word in some vector form. Okay, so this. So you can use skipgram or SIBO. So in skipgram you enter the word and you want to predict these words that can be near to it. When you train this network, in the end you find this middle neurons that are in the center. So you can remove these parts and you can take this part and it will be representation of word. So why we need representation? We need it to show, to make some representation, because in the end you will use some machine learning algorithm and you want to find it's like you want to find it what is how they are close to each other or not, and find the words which are near or find the words which are opposite or something like this. So for this case we use this word embedding. You enter the word and you find its representation. It's mostly dense because it has about 30 features. So one problem with this word is that it okay, do it have a problem? Okay, so the problem is that for different words, So there, this is, I don't know which language is this, but maybe some Indian languages, indigenous of America. So they have some this very complex structure. So it's like қанағаттандырылмағақтарыңыздан in Kazakh language. So when you combine words in some to some word, actually in Kazakh language it's mostly some suffixes. It's not words, but some suffixes which can be added, and it can change the logic of the word. But in these languages, these things, I think they are actually words, and they are combined to make it. Oh, okay, so this is also can be considered. So they are like the words are combined into one word, and then they become one new word. So in Kazakh or Turkic languages, you have word and you add some suffixes in the end. Okay, suffix and the end, and it may change its meaning. So for example, here it's for Russian language, and you see that it's also has some differences from Russian English languages. What is the difference? Is that it has different word. It has many different forms of the word. So for example, word предложение can be in many different forms. Maybe you have seen the example of how you can say running in English, which is, so it's translations to Russian language. So бежавший, бегающий, etc. So there are many different words and difference. So what is the meaning? If you use word to vec, you have to use the direct real words. Like if you have cat and cats, they will be totally different words. And for example, if you do not have word in this training set, you will not be able to find it. So to do this, these people, Bayanovsky, Gurev, Julin, Thomas Mikov. Thomas Mikov was one of examples, inventors of word-to-vec. They proposed enriching word vectors with subword information. So we have word vectors, which was word-to-vec. Subword information is some information that is stored inside the word. So for example, this is skiing, the word skiing, and to represent it, you will use something like this. The word itself, like in word2vec, you have the word itself. Then you have something like this. This means the beginning of text, and you ski here. Then skiing, it's foreground skiing, keying, ing, and ing, the end of symbol. And then you you set these words skiing, ing, keying. So actually it's like very big vector, and it has word itself skiing. So you say in word2vec you had information about text only for text, for real text, for example, like this. Okay, so you have this one hot vector, it says. So here only words like from A to banana, C, etc. Many different words, and in some place it has the. So it's actually words, there is no subword. But in fast text you also add here subword information, ink, keying, and etc. And you put it, and then you enjoying. So you also put these words, and then you can multiply them and sum. And you can use n-grams between 3 and 6 characters. How many possible n-grams? So there is very big number of n-grams. To simplify it, they use hashing. So for example, they limit the size of n-grams. Like there is no all n-grams. You only find out the it's less than 2 times slower than the word. So it's very fastly trained. Short engrams are good to touch. So this is the how you compare them. For example, intrinsic evaluation. So for example, whole agreement. Okay, so this is how people say this similarity. It's from 10. And then for example for agreement it's this is one. I don't know actually its value, but they compare these two words and then they say it. So actually this fast text is good for languages which are not like English. So in English you know that there is no like it's Russian says падеж, so you can so when you have forms, different forms, you have one word and it may be in different forms. Like in Russian you have koshka, so it will be one form, so it will be have koshki, koshke, and etc. So for word to vec these things will be different, very different. But if you use fast text, you actually are solving this problem because they will be very near to each other. So for this Arabic, German, Spanish, French, Romanian, Russian, it can be good. I don't know if it is for Turkic Kazakh language, but I think it will also be good for them because they have some because you will be able to store this information. Fast text evaluation. So for example, for autofarer, it finds that the important engrams like far, farer, auto, crease. So these parts are like considered. So for example, transform. It says trans very important because mostly words with trans they have some meaning that they change. For example, transform, etc. So this is Elmo. So the fast text, if you want to combine all things, the fast text means that you will store information, some extra information in word vector, instead of when you have word to vec where you store only the word itself. Also, it is good for example, unknown words. Like in previous example, we had name identity recognition. So name and the entities, they are mostly like they are mostly not very popular. So for example, except Google, etc. But for example, people names like Kaskiren, they may be in training set you will not have word Kaskiren, but actually Kaskiren is not good example. But for example, for names like Savitbek, there was no Savitbek in training set, but for example there was some Kazbek and someone other Bek, and it can find out that Bek, Savitbek and Kazbek are something similar, and you can use it as some extra information about this word. So it will be like it will be considered something near to Bek, and when you train some algorithm, it will find out that it is important.